Hello everyone, welcome to this first lecture of this series of lectures on fundamentals of structural analysis. So in this first lecture, we'll try to understand idealization of structure. So before jumping into the main topic, which is idealization of structure, let us understand a very simple idea of structure. What is structure actually? So let us give an example. Suppose I am sitting on my building, right, on the floor of my building, any of the floors, maybe second floor, third floor. You are also watching this video at your home, at your office, maybe. So yes, there is a building, right? So this building, if you see, this building is made up of, suppose, beams. You see the vertical columns, you see the slabs on which we are sitting now. Then those slabs having, you can say, maybe marble tiles or vitrified tiles laid on those. Then we have the it's a brick walls on the beams, maybe AC block walls on the beams. Okay, so these elements, beams, columns, slabs, these elements are taking the loads of those tiles, the brick walls, right? So maybe there are other loads also, like outside there is heavy wind. So the wind, if you see, the structure is taking that force from the wind, right? That pressure from the wind, and it is standing still, right? It is not falling down. So the system that we have generated, we have created by assembling different elements like the beams, columns, slabs, right? By assembling it in a one place, and we have created one system which are basically taking different kind of loads, right? So that system is, we can call it as structure, right? So there are different kind of structures. I have just given an example of building. Here I have, you can say, attached three images. So you can see here we have one reinforced concrete building with masonry walls, brick masonry walls. Then we have a RCC tall chimney. Mostly in the industrial areas, you will see these kind of chimneys. You can see one steel structure, pre-engineered buildings. Generally, we call them those. So those are structures. Those are meant to take some kind of loads. Okay, the type of load will be different, right? So in this lecture series, our aim will be to understand the loads, the elements, how those elements behave when those are subjected to those loads. Okay, so now let us come to this topic, which is idealization. Why idealization of the structure required? So when we say structural analysis, it's nothing but to understand the behavior of any structural element. Suppose if I see this beam, if I say this beam I have, right? This beam I have here. So to understand how this beam is behaving when we are putting some brick walls on this beam, when we are connecting this slab, which also have brick wall at the edge of it, how this beam is behaving, how this column, where you can see this vertical column, which is having this beam connected to it, this slab loads are coming to this beam, then from this beam it is coming to this column, how this column is behaving. And when these are subjected to, this column beams are subjected to this kind of loads, what measure we need to take to, you can say to resist, or you can say to make those elements stand still, irrespective of having all the loads applied on those, right? So to make this decision, we need to understand first how these elements are behaving, right? So very, you can say, how these are resisting this force. So obviously there is some resistance being generated internally inside this elements, which we call actually internal forces. So by developing internal forces, these are resisting the external loads, right? So now there are basically three things. One is load, which is actually threat to the structural element of the structure, right? Then this load is applied on the structural element. So I will say that the load is applied on the structure, right? Okay, then these structural elements develop internal forces, right? Internal forces. Okay, so this is the work flow, or this is the flow how it is basically resisting the load that is being applied, right? So we will break it more, okay, into different conditions, then we will understand. So basically this is what we need to understand in structure analysis. Okay, how the load is being applied, how the structure is behaving, and what kind of internal forces are being developed in the structure to resist this load or this threat, right? So now why idealization is required, because if you see this beam, so basically this is a, if I draw this beam, it is like this. Okay, if I draw the beam like in 3 dimension, so it is something like this. Okay, a solid block connected to another solid block, like here we have the column, right? Now there we have some brick walls, right? We have some brick walls that we have can say laid on it. Now if you want to, you can say, idealize this element the same it is as it is. So what you can do, like you can have infinite number of sections in this particular element, right? You can develop section here, you can develop section here, you can develop section here, like you can create numerous sections here where you can say see the behavior of that particular section, right? And again, as a 3-dimensional, you can say, element, if you have to analyze it, the analysis process is going to be very complex. Again, if you see this brick wall, okay, this when we see analysis, we are going to analyze it before constructing it, right? We are not going to analyze it after construction, because if you want to make it first, suppose we consider some size and we have made it you can say using concrete and some reinforcement inside, I will come to that part also, and then we have put some brick wall on that, and then we are seeing if it is deflecting more, if it is fading, then it is not possible, it is not, you can say, practical, right? So you have to analyze it first, and after understanding the behavior, we need to make decisions regarding the design. That means how that resistance can be developed, and then we can actually finally make it like this, right? So now to analyze a structure or a structural element, a single structural element also, so this is a physical structure, right? This is a physical structure that we can see, but this physical structure can't be analyzed when we are have not made it actually. So we need to idealize this physical structure into some simple elements, right? So generally what we do in this particular lecture, I'm not going very deep, I'm just giving some overview. So generally what we do, instead of having a block like this, a concrete block like this, what we consider that this concrete block is basically a line like this. Okay, so this is a 2-dimensional, or you can say a 2D line, right? This line element. So you call these things as this as a line element, right? So this is a basically concrete block having 3 dimensions, having some properties, having some moment of inertia, having some stiffness, but we considered it as a line. It is also having similar properties, that we are assuming, right? Or we are idealizing. Okay, now we have this brick wall. Now we cannot make this brick wall, right, while analyzing it. So what we do, we calculate the load of this brick wall, and this brick wall is, you can say, uh, uh, is there throughout the length of the beam. So we consider a, you can say, uniformly distributed load, because the brick wall having uniform thickness, uniform height, so we consider as uniformly distributed load over this line element, and this load is equivalent to the load which this brick wall will be putting on this beam, right? So here is my load, okay, as uniformly distributed load. Okay, here I have a line element, which is actually in the real life physical structure, it is a beam, it is a three-dimensional element, right? So a block. So what we have done, the beam is being idealized as a line element, the brick walls are being, I can say, idealized as uniformly distributed loads on the line element. Okay, now when we have, if you see, suppose I'm just analyzing this beam and this beam is connected to this column, right? So there is some joint between the beam and column, right? There is some joint between the beam and column. So if you see here in this point, loads are applied on this beam. So if there is no resistance, if there is no resistance in this particular point, at this particular point, so the beam is fall down, the beam will come down like this. So obviously there is something which is resisting this beam to come down, right? So there will be some resistance here. So I would say this is my resistance, okay, vertical resistance, right? Now as we have applied this load and this beam is connected to these nodes, right, this node here, so it can rotate also, it can rotate also like this, right? But if we consider, or if we see, or if you want that this beam should not rotate about this particular point, suppose I name it as A and B, okay, and we want that, let me change the color of this, maybe some green color. So I have a resisting force, okay, because of which it is not coming down, okay, so we call it as, suppose, force vertical, okay, fine. And when this load is applied vertically, okay, so this beam can rotate about this point, and if it is not rotating, then there is something which is resisting this rotation. So this rotation will be happening in this direction about B axis, you see, about B point. But if it is resisting the rotation, then there is a resisting force acting at this particular point, which is resisting this rotation. Okay, so this resisting element, we call it as moment of the force, right? The you can say, what should I say, the force, or the when we idealize that there is something which is resisting the rotation of the structure, so, or rotation of the structure due to the applied load, so we call it as moment of the force, right? So this is my moment, which is resisting moment, right? Again, if we had, you can say, we have applied some force along this direction also, okay, if you see this beam, if you just pull this beam outwards, this will not come out, right? This will not come out of this joint. So that means there is some another you can say force which is resisting this point or resisting this joint to come along this direction, along the long direction of the beam. So there is a resistance along this direction also. So I should say, suppose, force along horizontal. So these are the resisting components due to which this beam is standing still, even though we have applied some load, right? So this you can say joint, which is not allowing this beam, or this joint of the beam, to go vertically down, to rotate about the B axis, or to move along the horizontal, right? So this joint, we can idealize it as a fixed joint. Okay, this joint we can idealize as a fixed joint. So what we are doing, we have a beam which is connected with a fixed joint. So what is the property of this fixed joint? So the property of this fixed joint is, it is not allowing any rotation, it is not allowing the vertical movement, it is not allowing any horizontal movement of this particular point B, correct? When this line element is subjected to loads. Okay, so here if you see, we have considered, or we assumed this beam as a line. We have assumed the wall as a you can say uniformly distributed load, and the joint between the beam and column we considered it as a fixed joint here. Okay, as a fixed joint here, having these properties. Okay, so now it is very easy for you to solve. Now it is very easy for you to understand, right? You do not have to construct the beam, right? So what you have to do from this physical model, this is my physical model, okay, or the physical structure I should write, physical structure. Now we have got our idealized structure. Idealized structure. Now when you have this idealized structure, so it is something like this. Suppose this is my fixed joint, I have a line, okay, I have these 2 points, okay, so this is suppose B, this is A, and I have a uniformly distributed load applied on this, okay, uniformly distributed load applied on this, having some value. Okay, now what you can do, now you can generate or you can create mathematical expression of this. So now you can create mathematical expression for this, and then from this you can you can find out the solution. Now what are the solution? What we need actually in this solution? We basically need these internal forces. We basically need this internal forces. So these internal forces, so basically this FB we call it as shear. This you can say MR, it is basically the moment of force, or you can say the moment. This FH is basically the axial force, right? So these are the what we want in this case. We want these internal forces, how, or you can say what amount of these internal forces are being developed in this, you can say beam, and to resist, or you can say to resist these internal forces, how the section need to be developed. So that will be doing in the design part. Okay, so once we understand how it is behaving, the extent of these internal forces, so then only we can proceed with I can say the design, right? So here basically we are doing the structural analysis. So now you can understand the importance of idealization. If you are not able to idealize any structural element or any structure into a simple idealized structure, then it is impossible, because you cannot make a structure, apply the load, and check the I can say behavior, right? You have to first mathematically solve it. So for that you need to simplify the physical structure to a idealized structure. Okay, then you can generate the mathematical expression, and then you can solve that mathematical expression to find out the internal forces, right? Similarly in this chimney, in case of this chimney, so this chimney is nothing but a vertical cantilever. Now if you see, so this is a vertical cantilever like this, okay. Now if you see more precisely, this chimney has mass, right? This chimney has some load, right? So when we have you can say seismic activity, or you can say earthquake or wind applied on this you can the face of this chimney, surface of the chimney, so this mass will be moving, right? So you can have some lump of mass at every I can say you can at certain distance, right? So maybe this one M1, M2, M3, M4, M5, M6, M7, M8, M9, right? If you see this particular pre-engineered building, we can idealize it as a combination of lines like this, line elements like this, and some joints which are connecting these lines having some property, okay. I should not write like this, it depends on how you want it actually. Okay, maybe this side it will be fixed. Okay, so these joints will have some you can say properties like this. What are the things you want to resist, right? And similarly, we need to develop the physical model or physical structure also. Okay, the physical structure is basically representation of our idealized structure. Okay, or you can say the idealized structure is basically the representation of the you can say physical structure. Okay, so the if you take this joint, if you are allowing rotation, if you are allowing you can say axial force transfer, okay, the same should be there. The idealization of the this joint should be the similar. Okay, if you are idealizing something, making something, then it will be like you are end up doing some very you can say bad what should I say, you'll be ending up with a failed structure, or very what should I say, the behavior you will be evaluating, it will not be the same in the physical structure. So obviously when the behavior you have evaluated is not the same, then the design will not be correct, right? So that can lead to catastrophic damage, or you can say failure of the structure, right? So that's why when we'll be idealizing the structure, we need to understand how the joints, the loads, the structural elements are behaving, or should I say not behaving, like how those should be correctly idealized, and then only we can jump into the mathematical, generating the mathematical expression, and go for the solution, right? So this is the simple idea of idealization of structure. Okay, like if you see, if I just open a structural model, you see here, so this is a structural model, analytical model we call this, right? So this is basically a building like this. Okay, this is basically a building like this. I have idealized this building into if you see these lines, which are beams and columns, and these are two-dimensional, if you see, these are two-dimensional planes, right? So these are planes which are actually representing the behavior of the slab, the concrete slab, right? So these elements should have that property which will be similar to uh, 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 the physical structural element, right? And these joints which are connecting these elements should also represent the joint between the physical members. Okay, then what we have done, we have applied the loads. So this load that you are seeing is not actually loads, are basically the brick walls that we'll be putting in the physical model, physical structure, right? So here we have idealized the brick walls into, you can see, uniformly distributed loads on the beam, correct? So when we say idealization of structure, sorry, when we say idealization of structure, let me open that. Yeah, when we say idealization of structure, so it is not only idealization of the structural element, but also idealization of the loads, idealization of the joints, supports, everything. Okay, everything you have to idealize, which is basically or nearly representing the physical model or physical. Okay, so basically to simplify our work, or simplify the structural elements, simplify the loads, okay, we create this idealized structure, right? I hope it is clear to all of you. So whenever we'll be doing structure analysis, suppose in your office you want to you can say idealize this, you can say, should not idealize, you want to analyze this chimney. So it is not possible for you to construct the chimney first and then analyze when see how it is behaving under the wind, right? So first of all you have to do mathematical you can say solution. So to do the mathematical solution, you need something, right? You need something to solve. So that's why what we do, we idealize this chimney as a line with having some mass at certain height, and then we apply the loads, and we try to understand how this line with certain with the masses at certain heights, how it is going to behave, right? So this is what we do in the structure analysis, correct? So the basic, at the very beginning of the structure analysis, this idealization of the structural elements are very important, or idealization of the structure. not structure element. The whole structure, including the loads, the supports, the joints, is very important. So I hope it is clear to all of you what is the idealization of structure. In our upcoming lectures, we'll try to understand this point in more in depth. Okay, and we will see how we'll be finding out the loads, the, you can say, internal forces due to the due to the applied loads in the structural elements. So I hope it is clear to all of you. If you have any doubt, you can always write me in the you can say comment. Thank you, and see you in the next lecture.